Hello, all. Thank you for providing us the opportunity to present our work in IEEE International Conference on Flexible and Printable Sensors and System 2020. My name is Shahid Malik. I'm from the Indian Institute of Technology, Bombay, and this work was done in collaboration with Tufts University, USA, with Professor Sonkusale. So the title of our work is to design a fringing field-based screen-printed flexible capacitive moisture and water level sensor. So the idea was to design a sensor which should be disposable, should have low cost, should be fabricated using a easy fabrication process, and we should provide us an accurate measurement of the measurement. So the plan was to use the sensor in industrial application or agriculture application where we need a low cost sensor and low cost and disposable sensor because with low cost and disposable sensor we can use the multiple sensors in multiple locations, for example in agriculture application to measure the moisture or water level in the plant, in the field. And this was the motivation. And of course to obtain a low cost sensor we need easy fabrication process which should be simple and cost effective, and we should avoid the costly methods such as lithography and nano fabrications and these stuff. So we need a very simple fabrication process to do that. And one way to do the simple fabrication is using a screen printed method, which is quite simple, which only need a mask of electrode to fabricated sensor and a ink or the conductive ink to design the pattern, and which can be multiple sensors can be fabricated using this technology. So this is the simple fabrication process. We have done the fabrication using screen printed method. So basically polyamide substrate was used for the sensor design, and this polyamide substrate is flexible in nature. The pattern was designed on the polyamide substrate to fabricate the interdigitated structure. So the idea was to use the fringing field on the between those electrodes. So this pattern was designed using laser cutting techniques. So the electrode were designed, and then a stencil was printed, and the stencil was placed onto the polymer substrate. And then we have peel of the stencil, and only those pattern was printed on the polymer substrate. So this is shown here in the here. And then those carbon paste, which is conductive paste, was printed or pasted on the polymer sheet, and the and the electrode or the stencil was completely peeled off. So the pattern of the electrode or carbon paste was onto the polymer substrate. So in this way we obtain the interdigitated structure of the capacitive sensor onto a polymer substrate. And then in order to bring the fringing field and in order to avoid the contact or shorting of the electrodes due to water level or soil moisture, we have placed an adhesive tape on top of on top of the on top of the screen printed electrodes. So in this way, if there's a water level or soil moisture on top of the sensor, the fringing field between those electrodes will change, and which will change the capacitance of the sensor. So in this way, we can measure the water level or the soil moisture across the sensor. So this can be represented very well in this diagram, where this is a polymer sheet, and we have fabricated a pattern of interdigitated electrode using a screen printed method, and then an adhesive tape was placed on top of it, and two electrodes were taken out for the connection with the circuitry. So the total dimension of the fabricated sensor was around 30 mm of length and 20 mm of width. The separation distance between each fingers of the interdigitated electrodes was around 1 mm, and the carbon coating on top of the electrodes was around 0.8 mm. So the sensor was quite small in size, not very large, and which can be easily uh, placed inside the quantity or the target where we need to measure the water level or soil moisture. So this is the geometry of the sensor. Here we can see the actual fabricated sensor with a dip of water on top of it. So we can see the polyamide substrate here and the coated interdigitated electrodes on top of the polyamide substrate, and the adhesive tape can be seen also on top of the electrodes. The adhesive tape was not placed on tip of the sensor to make contacts with the detection electronic circuit or signal conditioning circuit. Of course, the water level is not in direct contact with the interdigital electrode. So basically, the fringing field between those electrodes is changed because of the water level, and which in turn change the capacitance of the sensor. So the idea is very simple, and the fabrication process of the sensor also is very simple in this aspect. So now we can see that the sensor contain a layer of interdigital electrodes around it, and of course the measurement is a conductive liquid or soil moisture. So the conductance between those fringing field, or basically we can say leakage resistance between those fringing field, will also change. Between those interdigital electrode will also change in according to the measurement. So this leakage is very non-linear, and it should be compensated in order to measure the capacitance of the sensor accurately. If you don't measure the leakage resistance, it will add up into the measurement, and which will give us the wrong information about the water level. So this should be taken care at the circuit level. So we have designed a signal conditioning circuit, which basically is a combination of phase sensitive detection and autonulling technique. So which utilize a bridge kind of structure where one arm of the bridge contains the sensor and another arm of the bridge contains the or utilize the reference uh, capacitor, which value can be controlled automatically using a feedback loop. So the idea was to equate the current quadrature phase current between the between the sensor and the and the reference capacitor. So here in the first of all we have to see the electrical equivalent circuit of the sensor. So this Cx is the sensor capacitance, Cp1 and Cp2 are the leakage or parasitic capacitor, and Gx is actually the leakage current or conductance which we need to compensate. So the idea is to measure the Cx only while compensating Cp1, Cp2 and Gx. So this circuit was designed to actually compensate Cp1 and Cp2 as well. So if you see Cp2, one terminal of Cp2 is connected to ground, another one is connected to the virtual ground of op-amp I2. So there is no current flowing into Cp2. So the capacitance Cp2 will not affect the circuit. And in this way Cp1 as well, if you consider that input impedance of the signal source is quite low, so of course there won't be any effect of Cp1 into the circuit. So now the deal was to compensate Gx or the leakage conductance and measure the sensor capacitance accurately. So this was done by converting the current into the sensor and reference branch into an equivalent voltage, and then phase shift. Then this voltage was modulated to a higher frequency using a quadrature phase shifter and a phase sensitive reduction switch based technique. So this switch will modulate the information from the sensor into the DC, and the leakage resistance will get shifted into a high frequency. This high frequency component was then removed using low pass filter, and the capacitance and the loop will continuously integrate the value of this low pass filter output till we get a current equal to the sensor information. So at the balance condition, when the output of the low pass filter is 0, we can obtain information about the sensor capacitance, which can be given by this equation: Cx equal to Cs into V reference upon Km. Here Km is the gain of the analog multiplier, which is given in the volt. So in this way we can, if we have a value of V sense, which is the output of the integrator, we can simply obtain W of the sensor capacitance since Cs is the non-capacitance. So this is a very simple and effective circuit to compensate the leakage and parasitic capacitance of the sensor and to measure the sensor value very accurately. So once the signal conditioning circuit was designed, we have integrated the sensor with the signal conditioning circuit and measured the output of the sensor at different water levels. So this can be seen here. The auto balancing circuit was fabricated using a PCB, and here we can see the fabricated flexible water level sensor placed inside a bottle of water, and different level of water was placed using injection into the can, and the change in the capacitance was obtained and visible on the screen of the computer, where we have acquired the data using an analog discovery board, and we have measured the value of the sensor capacitance and different level of water level using using the expression we have obtained and the voltage we are acquiring from the auto balancing circuit. So the output shown here represent the change in the capacitance for different water level. Here we can see we obtained a very linear changing output. We have changed the water level from 1 mm to 10 mm, and we have observed the change in capacitance from almost 10 picofarad to 20 picofarad, which shows us that the variation in the capacitance is around 1 picofarad for 1 mm change in water level. And we can also see that the relative error of the circuit is quite low. You see it is around the maximum is around 4%, but if we see very carefully, it's for water level from 2 mm to 10 mm, it varies in plus minus 1 or 1% of relative error. So the system actually provide very accurate information thanks to the auto balancing circuit and the fabricated sensor. So the conclusion is we have fabricated a very low cost sensor for water level measurement based on fringing film, and the sensor is interdigitally structured on to a polyamide substrate. The screen printing was used. A robust signal conditioning circuit was designed to sensor, and sensor provide measurement very accurately with very high sensitivity or reasonably well sensitivity. This sensor can be used in low-cost industrial and agriculture application. So the future work is to analyze the different source of errors and to further reduce the error of the sensor in the measurement. Thank you for your attention.